Hello, everybody. So today we're going to talk about the reactions of amides. And so amides are important in biology because they form the functional groups that forms the backbone of proteins. So the peptide bond and um, the peptide bond of the protein backbone is an amide bond. And it's because amino acids have their carboxylic acid side, their amine side. You can put basically snap amino acids together by forming amides from amines and from carboxylic acids. And so these are usually synthesized, not of, but from acyl chlorides. So the same way everything else has been synthesized, all our other carboxylic acid derivatives, is we use acyl chlorides to synthesize them generally because it's so easy and they're so reactive. And so the amides from an acyl chloride, we can get a different classification of the amides. We can have different substitution patterns. So we can either have mono or disubstituted amines, right? So we can have an amide, which is just hydrogens, right? So if we have ammonia as our nucleophile for the nucleophilic acyl substitution, we will end up with a unsubstituted amide. If we have a primary amine as our nucleophile, oops, let me put that a little bit better with the reaction arrow, R prime, NH2. This will give us a monosubstituted amide. And then if we have a secondary amine, R prime, oops, and R double prime H, this will give a disubstituted amide. And the tertiary amines, again, will not form amides from an acyl halide. We talked about that with our acyl halides, just because we do need that deprotonation of the H there, and it's easier to abstract a hydrogen than to break a carbon nitrogen bond. And so similar to esters, amides can go through a lot of the same chemistry. They can undergo hydrolysis and then a different type of condensation reaction to then bring amines and carboxylic acids together. But a lot of times, especially if we're looking at catalases or any enzymes that degrade protein structures, they perform the hydrolysis of amides. These are going to be a little less reactive, so generally they require a little bit more um, require more energy to do. Requires more energy to do in these cases. Right, so these are the uh, different types of amides we can synthesize. They're usually synthesized from acyl halides. All right, so we can have, again, two different types of uh, hydrolysis of amides. We can have an acid catalyzed hydrolysis or a base catalyzed hydrolysis, and the mechanism is almost identical to what it was for esters. Um, Here is because we require more energy, usually we need more extreme, so higher temperatures, high pressure, extreme conditions for the reaction to proceed. But overall, the mechanism is relatively similar. So we start with an amide, have a unsubstituted amide here. We're going to basically create a carboxylic acid and ammonia, but if it's a substitute amide, we'll get an amine and a carboxylic acid. And then if this is going to be acid catalyzed, we will protonate the carbonyl carbon. And when we do that, it'll allow for nucleophilic attack of water of this protonated intermediate, NH2, like this. Then we get our tetrahedral intermediate when this happens. And again, similar to esters, most of these steps are going to be reversible. And so we get a tetrahedral intermediate, carbonyl, H2, N2H, and then O. And it's going to be a positive charge on this O here. OH like that. So then we'll get proton transfer basically from the H3O plus, or not H2O plus, but this positive charge H2O that's bonded to the carbonyl compound. So this is going to be proton transfer. This is going to give us an H3 now with a positive charge there. This can stabilize the positive charge a little bit better than the um, alcohol can. And when this happens, this NH3 becomes a good leaving group. We can get water, can come and take this proton, move the electrons back down to the carbonyl, and then the amide can leave, or the amine group can leave. And so we're going to have ammonia as a byproduct because it wasn't a substituted amide at all. And so now our final product will be a carboxylic acid plus ammonia here and acid. And if we have, right, so this is going to also give us H3O plus, and these two can then react with each other so that the reaction stays neutral, right? Because so the carboxylic acid is fine, it'll stay the same, but then we can have ammonia, which acts as a base, and H4 plus, and then H2O, right? So we don't generate H0 plus in solution because the ammonia reacts with the H3O plus before it can change the pH of the solution. Okay, so that's the acid catalyzed hydrolysis of amides. We can also similarly have the base catalyzed hydrolysis of an amide, which is very similar to what it was for esters. Again, we're going to have the nucleophilic attack of the base on the carbonyl carbon and then go from there. Start with our amide. And we can do a primary amide just to switch things up a little here, or monosubstituted amide. We have our base in solution, which will then attack the carbonyl carbon and then generate our tetrahedral intermediate and H R prime O minus, right? So we get our tetrahedral intermediate. Simple leaving of the amino group as the generate the carbonyl. So we get our carbonyl generated again, and then we have OH plus our now negatively charged primary amine. In this case, so we N R prime H, and this is going to be negatively charged. This is going to be extremely basic, so this is going to come abstract the proton. If we are basic conditions, we will have a carboxylate instead of a carboxylic acid. We'll have the negative anion the same way we did for esters. We'll have a carboxylate ion. So then we get that plus R prime H2N. Right, and so we generate our carboxylate ion and our either primary amine, ammonia, if it's just not even a primary amine, but just ammonia molecule, or a secondary amine if it's a disubstituted amide, right? So depending on the substitution of the amide, if there's no substitution, unsubstituted amide, then we just get ammonia as our byproduct there. Most prominent in when we have proteases that digest polypeptides, they form, instead of a tetrahedral intermediate, it's going to be an intermediate that's called an acyl enzyme intermediate, where instead of this OH group that I have here, we can basically have part of an enzyme bind here, cause the amide to leave, and then through various interactions with solvent, acid and base, or base, can then regenerate the enzyme at the end, right? So that's one of the
conditions for being classified as an enzyme. And so we can have base catalyzed hydrolysis of amides as well. The last reaction that we're going to talk about for amides is going to be the reduction of amides. And so similarly to how the carboxyl or carbonyl groups can be reduced to alcohols, amides are reduced to amines, right? So instead of creating or breaking carbon uh, oxygen bonds in the case of reduction, right? Breaking carbon oxygen is one way that we can reduce. We think of it in terms of gaining a carbon hydrogen bond. So we're losing a carbon nitrogen bond and gaining a carbon hydrogen bond. And so in this case, we have instead of a tetrahedral intermediate, we're going to have an iminium, or sorry, an iminium ion intermediate, which is similar to what we saw when we looked at aldehydes and ketones, and we looked at generating uh, imines and imides from aldehydes or ketones. We're going to have an intermediate, except it's going to be an ion. And so the reaction for how this is going to happen, or the mechanism, let me draw it a little higher up so I make sure I have enough room, is we start with an amide, and it can be monosubstituted or disubstituted. Let's do a disubstituted amide just because we haven't done that yet. And then we have our hydride ion in reducing conditions, which is going to make it slightly basic. And then we'll use ether as a polar aprotic solvent to then allow for no extra stable intermediates. And so all the mechanistic steps will be concerted in this way. And so we have nucleophilic attack of the hydride on the carbonyl carbon to generate our tetrahedral intermediate, which is then going to be stabilized by the aluminum hydride complex, AlH3 minus. So this is going to be stabilized by this. And then we have our hydride, hydrogen still there. And then we have our amide. So this is going to be R prime, R double prime. And this will then cause the leaving of this um, aluminum alkoxide compound right here. And then a double bond will form between the nitrogen and the carbon, what was the carbonyl carbon. And that's because this aluminum is very electron poor. So the oxygen is okay leaving to go try and stabilize those negative charges there. So this is going to form a double bond, which is then going to create our iminium intermediate. That's our hydride proton still there. And then we'll have a positive charge on this nitrogen, R prime and R double prime. So now we have our iminium ion, which can then be attacked again by a hydride. And when that happens, that'll then neutralize, or not neutralize, it'll move the electrons from the pi system back onto the nitrogen to get rid of the positive charge. And then we end up with an amine, which is what we expected from the reduction, right? Our definition of reduction, right? So we have an extra carbon hydrogen bond from carbon hydrogen bonds that indicates that we've performed a reduction. And so this is the mechanism for the reduction of an amide into an amine. And so in a simplistic way, whenever you do a reduction of an amide into an amine, you're really just taking wherever the amide was and replacing it with, or get hydrogen, right? Where the carbonyl was, you're just replacing it with hydrogen molecules. And so that'll conclude all the different reactions that we're going to talk about for in regards to amides. The important thing to notice for this reaction is that we have our tetrahedral immediate, but then we also get an iminium ion intermediate as well. Okay, so next time we're going to talk about the spectroscopy of all these different carboxylic acid derivatives.